Hello guys, good morning. I hope you can hear me. So guys, today in this session, we are going to start with geometrical isomerism. Okay. Guys, geometrical isomerism is a part of stereoisomerism. Okay. So stereoisomerism, like you see, just a second. Okay. So I'll share the screen first. Yeah. So geometrical isomerism, guys, it is a part of stereoisomerism. Okay. Last class, if you remember, we have taken a session for isomerism itself for KVPY. I have given you the detailed classification of isomerism. How molecules are classified based on their isomeric structure or properties. Correct. So we have two different types of isomerism. First of all, structural and stereo. And stereo further classified into two types, that is geometrical and that is configurational and conformational. Right? Stereo classified into configurational and conformational. Conformational, we have one type. Configurational further classified into geometrical and optical. Okay. So we are going to see here, we are going to see geometrical isomerism today. Okay. So again, if I repeat this part here, we have, first of all, we have stereoisomerism. Stereoisomerism, which is of two types. Okay, that is configurational conformational. Configurational classified into two categories. That is geometrical and optical. Okay, conformational, we have one type. Okay, so this is the stereoisomerism. Okay, as far as J is concerned, all three types of stereoisomerism are important. Okay, geometrical, optical, and conformational. All three types are important. Okay, but KVPY, like I already said, there is no defined syllabus for this. Okay, geometrical and optical are the part of 11th grade, which we usually study after nomenclature in organic chemistry. Okay, but we are doing this a bit early because you are going to have your KVPY exam in last week of October or November first week. Correct? So we mainly focus on geometrical isomerism here in this session. Correct? So first of all, to understand this geometrical isomerism, first of all, what is stereoisomerism? Okay, stereoisomerism is the phenomenon by which a given compound exists in two different structural units in which the relative positions of atoms or groups are different in three-dimensional space. Okay, what is stereoisomerism? Stereoisomerism it is the phenomenon under which a molecule exists in different structural units in which the relative position of atoms or groups is different in three-dimensional space. So in the space, if their relative position of atoms or groups are different, this phenomenon is called stereoisomerism. Okay, and the different structures are called are called stereoisomers. Okay, stereoisomers. Now, this stereoisomerism, like I said, have mainly three types: geometrical, optical, and conformation. So we are going to see here geometrical isomerism. Here, geometrical isomerism. What is geometrical isomerism? First of all, we'll write down the definition here. The isomers or the compounds which possess the same molecular and structural formula, but differs in the arrangement of atoms or groups. In space due to restricted rotation around the double bond around the double bond or ring structure around the double bond or ring are called geometrical isomers. And this phenomenon is geometrical isomerism. Okay, so this is the definition we have. Okay, so what I said here, you see the restricted rotation across the double bond or ring. This is important. Okay, so first of all, what do we understand with this restricted rotation around the double bond and ring? Okay, so first of all, we'll try to understand this. Correct. So what is restricted rotation? You see, restricted rotation, for example, you see, if I write down this example, CH, single bond CH, CH3H, CH3H, CH single bond CH, HCH3, CH3H. Okay, this is first, this is second. One more example I'll write down. We have C double bond C, CH3H, CH3H, and the other one is C double bond C, HCH3, CH3H, these two structures. Okay, so first set of question is this, second one is this, 1 and 2. Okay, so if I ask you what is the difference in this two structure and difference in these two structures, are they same, are they different? If there is any difference, what is the difference? This pair of compound, and we are taking a pair of compounds here because isomers we only define in a pair. Okay, it is not absolute, correct? So it is not like we can say this compound is an isomer. Isomer of what? That makes sense. Okay, simply if you say this is an isomer, that does not make sense. Okay, isomers of what compound? So isomers we always define in a pair, correct? That's why I have taken a pair of compounds. See, when you look at these two compounds are exactly same. You just rotate this one, this way you can rotate, means if you rotate this bond like this, okay, this is fixed, and just you rotate this. This comes over here and H comes onto the CH3, you'll get this. This rotation will get you this. So these two are what? These two are identical compound. Same compound. These two are same compound, identical compound. The relation between them is what? They are identical, same compound. Okay, but can we do the same thing over here? This rotation, can we do that? No. Here the rotation is not possible. Rotation is hindered here. Why hindered? Because we have double bond present over here. So how this double bond forms? Double bond forms, I have already explained a bit here, by lateral overlapping of orbital. Means these two orbital overlaps, we forms a double bond, and we have a single bond present over here. Sigma is this, and this is pi, this overlap. So if you want to rotate this, okay, so if you want to rotate the bond like this, keeping this one fixed, this one is fixed, right? Because overall you can flip the molecule, entire molecule you can flip. But to get this one from this, what you need to do? You need to rotate this bond, this carbon you need to rotate, keeping this carbon fixed, right? And then only we'll get this. So if this is fixed, and if you want to rotate this bond, if you want to rotate a sigma bond like this, then obviously this bond you have to break, the pi bond you have to break. Then only it will rotate. Okay, but that is not possible. We cannot break the bond here, because for isomers, we must have same molecular formula. So bond we cannot dissociate. Hence, what we say that the rotation across double bond is hindered. Okay, rotation is not possible here. Here we have only single bond, there's no pi, so we can rotate this molecule easily. Like suppose you have a pen, the carbon-carbon bond length, you consider the pen. The two end of the pen is the carbon, right? So we can fix the one carbon atom and rotate the other one if it is single bond. But if it is double bond, right, then the rotation is hindered. You have to break the bond over here, correct? And dissociation of bond is not possible in isomers. Hence what we say, across double bond, the rotation is restricted, okay? This is what the restricted rotation. Across double bond, rotation is hindered or restricted. Rotation is hindered or restricted. Correct. Same restriction we have with ring also. With ring structure also, the rotation is hindered. And in this case, the geometrical isomerism is possible. In the first case, it is not possible because both are same atom. Okay. So when you rotate, in the first one you see, when you rotate the carbon atom, that won't affect the property of the molecule. It has the same property. Because the relative position is actually not changing here in the first one. Okay. A relative position means the position with respect to this carbon, this carbon, this carbon, this hydrogen and other things. Okay. But here it is happening. You see this distance and this distance. This distance is obviously more than this distance, right? So the relative position is hindered over here. Correct? So in this case, GI possible. These are identical. GI not possible. Okay. Now the same example I'll take to make you understand one more thing over here. Suppose I have taken the same example. We have CH3. Just a second. Suppose we have taken CH3, C double bond C, CH3, H and H. C double bond C, C, H here. Here we have CH3 and here we have H. What is the IUPAC name of this compound? IUPAC name that you can do easily because we have done it already. The IUPAC name of this compound. The IUPAC name is but2-ene. And this one is also but2-ene. Okay, same name we have. Now the thing is, we have already discussed that these two are different compounds, okay, and they show geometrical isomerism. So they are basically, they are GI, geometrical isomers of each other. Geometrical isomers of each other. So it means they have different properties also, different physical properties. So properties also we'll see, okay, they must have different physical properties, okay. So the two compound, we can say these are different compounds, these are not the identical or same compound. Now you see the purpose of IUPAC, the various rule that we have discussed, the purpose is what? That each and every compound should have different names, so that with one name we'll have only one compound, so that we can understand it, okay, that what compound is given in the question, correct? So here what happens, this in case of geometrical isomers, you see the two different compounds which has different physical properties, they have same IUPAC name, right? So they have same IUPAC name, so the whole purpose of IUPAC is defeated over here, correct? Because we have two different compounds have same name, so the whole purpose is defeated. So what we do here to resolve this, okay, to solve this, to resolve this, what we have done, we are taking, we have given a term here, so that we can easily understand that which compound is given and what is the name of that compound. Okay, like the term is what? If the two identical group, like CH3 HH, if two identical group are on the same side of the double bond of carbon atom, okay, if the two identical group, what I have written, if the two identical group present on the same side of double bond, if the two identical group present on the same side of double bond, the compound is called cis isomer. Okay, cis isomer. If the two identical group present on the opposite side, in short I'll write down here, present on opposite side, then the compound is trans isomer. Trans isomer. Okay, so you see the two identical group present on the same side, so it is cis isomer. And this one, the identical group present on the opposite side, so this is trans isomer. Okay, so the name of this compound is trans 2-butene, and this one is cis 2-butene. Now suppose the benefit of this particular terminology is what? Suppose if I ask you to draw the structure of but2ene. But2ene. The structure, some of you may draw this. Some of you may draw this structure. And some of you may draw this. Okay. Okay. So okay. So when you have but2ene, you can draw this structure or you can draw this also because it's not clear. Okay, because it's not clear that which structure you have to draw. And we cannot draw the both structure here. For this question, we can draw but2ene. This is also but2ene. But actually, we cannot differentiate that which one we have to draw. Okay. Now, if I ask you, draw the structure of cis2butene. So obviously, you'll draw this side because we know cis we use when the identical group present on the same side. So this is again cis2butene. If I ask you to draw trans2butene, you can draw this structure easily. Okay, so this is the benefit of these two terms that we are using here, trans and cis. Okay, so some more example you see. This compound, you see the molecular formula is same. This compound we call it as, the name of this compound you must remember, malic acid. This is malic acid. This one is fumaric acid. Okay, so malic acid and fumaric acid are geometrical isomers of each other. If they give you the structure, the chances are less. Okay, then you can easily say they are geometrical isomers. But then when they ask you the name, what is the relation between malic acid and fumaric acid, and probably you won't say because you probably do not know the structure of the both compound. Correct? So that's why I would suggest must remember the structure of malic acid and fumaric acid. What is fumaric acid? Fumaric acid is the trans form. Okay, it is a trans structure of this one. And this one is the cis structure of this one. Okay, this is again important, correct? Transform fumaric and cis form malic. Malic, fumaric, both are geometrical isomers of each other. Okay, one more example you see, we have C6H5 benzene ring here, C double bond C, COOH, hydrogen and hydrogen. Okay, C double bond C, H, H, COOH and C6H5. Okay, this compound is again cinnamic acid. cinnamic acid. This is also cinnamic acid. Cinnamic acid. This is the cis form. Why cis? Because two hydrogen on the same side, identical. So, and this one is trans form because two hydrogen on the opposite side. So with respect to hydrogen, we can say, but the other two groups are different in this compound. Okay, the other two groups are different. This compound is what? This is substituted alkene. Okay, substituted alkene is what I'll tell you. Suppose we have CH2 double bonds, CH2 double bond, CH2. This is ethene. Okay, CH2 CH3. This is prop-1-ene or propene. So ethene and propene, here it is more substituted alkene. It is substituted alkene, we can say. Why substituted alkene? Because one of the hydrogen is substituted over here. One hydrogen is replaced by methyl. It is substituted alkene. One more hydrogen you replace, you'll get this CH3 CH double bond CH CH3. This compound is even more substituted than this. Okay, it is more substituted alkene. More substituted alkene. Correct? So this is what this is, more substituted alkene. So this is what this is the this alkene, and this alkene. These are obviously not geometrical isomers. Right. These two are not geometrical isomers. In this geometrical isomers not possible. These three are also not isomers of each other because the formula is not same. But yes, this one is ethene. This is substituted alkene, one hydrogen replaced. This is more substituted alkene. Like this, if you keep on substituting hydrogen, you will get more and more substituted alkene. Correct? So when you have substituted alkene, then preferably we don't use cis and trans term, but we use E and Z system. Okay? So write down, in case of more substituted alkene, we preferably use E and Z system of nomenclature. E and Z system of nomenclature. Now, what is this E and Z? First of all, this E and Z has nothing to do with cis and trans. Write down this one. E and Z has nothing to do with cis and trans. This means what? E can be cis, E can be trans. Z can be cis or Z can be trans. All possibilities are there. Now, how do we define, how do we assign this E and Z isomer? Right? To assign E and Z isomer, suppose we have this molecule. Suppose we have carbon-carbon double bond, and on this groups are attached PQ, RS. This is the most substituted alkene because all the hydrogen has been replaced. If I write down this C double bond C, PH, QH, this is also substituted alkane because these two groups are different. But this one, with respect to hydrogen, we can say it is cis also, because identical group or atom on the same side of the double bond cis. But how do we assign E and Z isomers first of all? Now, first of all, to assign E and Z isomer, we have to assign priority on the group attached to the double bonded carbon atom. So first of all, we assign priority on the atom or group attached to double bonded carbon according to CIP rule. Okay, so we will assign priority according to CIP rule. So what is CIP rule? Okay, that we'll see. But suppose we have assigned the priority here, and the priority we get, suppose P has more priority than Q. So this is 1, this is 2. Suppose S has more priority than R. So it is 1, it is 2. So we'll assign priority on this two. We'll compare this two for priority. We'll compare this two for priority. It's not like we are comparing this two. So we'll compare the atoms or groups attached to the double bonded carbon. Means this is the double bonded carbon atom. So we'll compare these two atoms or groups and these two. So suppose P has the higher priority than Q and S has the higher priority than R. Okay. So if higher priority are on same side, so it is Z isomer. If higher priority are on opposite side, so it is E isomer. Z or E isomer. Correct? So this way we can do. Okay, E and Z isomers. So we'll assign the priority first. Correct, into this. Priority according to what? According to CIP rule. What is CIP rule? CIP rule we'll see. Okay, so we'll assign priority. If higher priority on the opposite side, it is E. On the same side, it is Z. So for example, this one you see, this one is cis already with respect to hydrogen. If this P has more priority than hydrogen, and this Q has more priority than hydrogen, right? So higher priority on the same side, this one is Z isomer. And this one is E isomer. Z and E isomer. So you see Z and cis, both possible for this one. But preferably we use what? If the alkene is more substituted, okay? Then mainly we use E and Z system, not cis and trans. But if they ask you whether it is cis or trans, the answer would be cis with respect to the hydrogen. Okay, fine. Now we'll see first, because you need to assign priority to understand E and Z isomer. So for that, you should know what is CIP rule. Okay, and according to CIP rule only we'll do this. Okay, so CIP rule is what? CIP rule, we also call it as, sequence rule. Sequence rule, both are same thing. Correct. So there are few, rules given in this that you need to keep in mind, and that is it. You have to follow that rules and assign the priority. So first one is what? Higher priority, sorry, higher atomic number will have higher priority. For example, if iodine, bromine, chlorine, fluorine are attached to the double bonded carbon atom, then their priority will be this according to the atomic number. Okay. If you have isotopes, in case of isotopes, we'll see the mass number. We'll compare mass number, not atomic number for isotope. For example, we have tritium, deuterium, and protium. Mass number is maximum for tritium. This is the priority order we have. Suppose we have O18 and O16. The priority will be more for O18. Okay. Suppose you have chlorine 37 and chlorine 35. The priority will be more for chlorine 37. Right? Like this, you assign priority for isotopes. Third one, if groups are attached, then we'll assign the priority on the basis of the atomic number of the first atom. For example, you see, we have chlorine attached, SO3 attached to the double bonded carbon atom, and then we have OH attached to the double bonded carbon atom. We have NHCH3 attached to the double bonded carbon atom. We have COOH attached to the double bonded carbon. If these are the groups attached, okay, then we'll compare this on the basis of the atomic number of the first element. The atom which is attached to the double bonded carbon, sulfur, oxygen, nitrogen, carbon, right? So you see the atomic number of chlorine is what? It is 17. Sulfur, it is 16. Oxygen, it is 8, 7, and carbon, it is 6. So the priority order would be this. More atomic number, more priority. Correct? Now what happens sometimes, two groups has the same atom attached with a double bonded carbon. For example, if this is the group attached, CH2, CH3, this is the group attached, another one is CH3, and another one is COOH. If these groups attach to the double bonded carbon atom, then what we'll do, see, the first atom is carbon only here, right? It is 6, it is 6, it is 6. So first atom is same. If we cannot decide on the basis of first atom, then we compare the second atom in the parent chain. And that is carbon. After carbon, we have carbon only. And after carbon, we have hydrogen. See here, we do not have any choice over here. Generally, we consider the primary chain, the main chain, we consider 1, 2nd, 3rd, 4th, like that. But if there is no primary chain like this in case of methyl, then we do not have any other choice. We have to compare hydrogen only over here, right? So carbon, hydrogen, carbon has more atomic number. So the priority order of this is more than this, okay? So first of all, we can write CH2, CH3. Its priority is more than CH3, okay? First atom is carbon, second atom is oxygen, right? Oxygen, hydrogen, and carbon we need to compare. Oxygen has more atomic number, so COOH has the highest priority in this group. Okay, so this is what we do when we have first atom same in the groups attached to the double bonded carbon. This is what we do this. Okay. Now, for example, you see, assign E and Z isomers into this. E, Z, if possible, you can also say cis or trans. Okay. So, for example, you see, we have double bond here. Double bond. Now, when you look at this molecule, okay, so this is CS3 and this is this propyl group. This side and CS3 this side. Obviously, this side we have hydrogen and this side we have hydrogen. Understood. Similarly, here also we have hydrogen and hydrogen. This is understood, right? Okay. However, it is not given. Correct? Because it is a bond line structure. You know, in bond line structure, we do not represent carbon-hydrogen bond. Okay. So, but this, I have written these hydrogen here to make you understand this. So, you see one side we have methyl and another side we have carbon, 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 and hydrogen. If you assign priority on this methyl has higher priority than this hydrogen, and this propyl has higher priority than this hydrogen. So higher priority on the opposite side, correct? So it is E isomer. It is E isomer. Here you see the higher priority are on the same side, so it is Z isomer. E and Z. Preferably we can write this. In terms of cis and trans, if you see, both identical group, hydrogen on the opposite side, it is trans, hydrogen on the same side, it is cis also. Okay, one more example I'll show you. Suppose we have this molecule. Okay, this molecule we have. Okay, so here also you see, we have one hydrogen present this side and one hydrogen we have this side. This has 2 carbon atom, only one, and this is 1 carbon. So obviously, if you assign the priority here, it has 2 carbon atom, more priority than this. It has more priority than this because carbon, hydrogen we need to compare. This one also has more priority than this. This one has more priority than this. Higher priority on the opposite side. So this one is E isomer. And this one is higher priority on the same side. It is Z isomer. In terms of cis and trans, what we can write? Identical group do we have into this one? Yes, we have methyl. 2 identical group on the same side. So this one is cis. 2 identical group on the opposite side. This one, opposite side. So it is trans. Always keep that in mind for for cis and trans. We don't see the priority order, but we'll see the groups are identical or not. If all the 4 groups are different, then we cannot say that these are cis isomers. Even if the 3 groups are different from each other, right? For cis and trans, at least 2 groups must be same. Okay, at least 2 groups will be same. But whenever we have more substituted alkene, we consider what? We consider E and Z a terminology, not cis and trans preferably. Okay, so I hope you understood this. Fine. Another one you see, one more example we'll see in this. Suppose we have C double bond C, chlorine here, CH3 here, and then suppose we have OCH3 attached to this, and here we have hydrogen. Try this too. Okay, so what we'll do, we'll assign priority first of all. 1, 2, oxygen 1, and this is 2. Identical group on the same side, correct, sorry. Higher priority on the same side, it is Z isomer. In this one, cis trans is not possible. In this one, you see, first of all, this is 1, this is 2, chlorine and carbon, carbon and hydrogen. This is also Z isomer. This is also Z isomer. And in terms of cis and trans, if you see, it is trans also. So you see, Z can be trans and Z trans, E cis. The previous example, if you see, we have E trans and Z cis. That's why I told you that this E and Z has nothing to do with cis and trans isomers. E can be trans, here you see E trans, and E can be cis also. Z trans and Z can be cis also. Okay, so all these possibilities we have, correct? Now, the next thing here, if you have molecules like this, carbon nitrogen double bond, we have one lone pair here, one hydrogen, we have CH3 and chlorine, like this. Achha, we'll discuss this later. We haven't discussed carbon nitrogen double bond. We'll see this. Okay, now you see we have carbon carbon double bond. Here we have CH3 and here we have CH3. This side we have hydrogen and this side we have OH, suppose. This one, if you ask me to say isomers into this one, so what you can do, this is 1, this is 2, this is 1, and we cannot assign priority into this one, okay, because both are same, right? Priorities we cannot assign into this one. That's why in this one we cannot define isomers, so no GI into this one, no geometrical isomers, okay? And this is the condition for a molecule to show geometrical isomers. If this two group, this one, means the two atoms or groups attached to the carbon atom, to the same carbon atom, to the same double bonded carbon atom, since these two are identical, same group attached, then GI, geometrical isomerism, is not possible. Then geometrical isomerism is not possible. And hence there is no point of assigning this thing, priority onto this, okay? So what are the conditions for a molecule to show geometrical isomerism? Okay, that is the next concept we need to understand. There are 3 conditions for this, okay? So those conditions we'll see in the next session. Thank you so much. Take care.